Hi, folks. Welcome to chapter number 8, the measurement of high test voltages. Obviously, the measurement of high test voltages would take place in the laboratories. The like generation of high test voltages, measurement of high test voltages is also very specialized uh, technique. You have to apply to your requirement uh, the techniques because you will need to be very accurate in the measurement, and the level of voltages is very high, and you have to have the continuous measurement of voltage in case of DC and AC, so that you can stop the application of the voltage wherever you want. Then in case of lightning and switching impulse voltages, or in general for impulse voltages, the waveform must be the oscilloscope must be there to provide you oscillograph of the waveform, because you have to produce a certain waveform as prescribed by the standards, and the waveform recording or waveform uh, saving on the oscilloscope uh, is also very much desirable. These techniques were difficult in the earlier days, say about 50 years back, but today the gadgets, the measurement techniques and gadgets have advanced like anything. So storage oscilloscopes and the quality of oscilloscope to give you the waveform is easily recorded. When you do measurements like partial breakdown measurement, you have to also record the partial discharge pattern. You may have to determine the inception voltage, extinction voltage, etc. So the measurement of voltage, high test voltages, is a very vast field, and a lot of work has gone through. One of the simplest way of measurement, you would say, see one thing, you cannot measure, say, at 1000 kV. How could you measure at 1000 kV? It's such a high voltage. Your instruments always work on something around 100 to maximum 200 volts. So how to measure a very high test voltage to the order of 1000 kV or more of that high voltages? You have to bring down the level of voltage at which you can measure. Desirable level to which you bring down the level of voltage is around, as I said, 100 or 200 volts. So in one way, if the input voltage is not very high in a, say, AC power frequency transformer, you just measure from the primary side of the transformer. That is adopted by many people. But again, it is not very exact. If you calibrate uh, on paper with the turns ratio of the transformer, I'm talking about first the AC power frequency measurement. You calibrate the primary side with, you just make use of the transformation ratio of the transformer, and calibrate the dial accordingly, uh, and measure the voltage from the primary side, which is much lower. Then uh, that is not accurate. Why? In our particular case of measurement of high test voltages, when you test a high when you test an apparatus, as I've been mentioning, you apply the voltage on the capacitor or the capacitance formed by the insulation, because you are investigating the performance of the insulation provided on the apparatus. So what you are basically testing, the electrical parameters, you are basically testing the capacitance. And whenever on a transformer there is a capacitive load, what would happen if on a transformer there is a capacitive load? What would happen? Just a minute. Yeah, uh, we I'll explain it to you. What would happen if you have a transformer and the secondary voltage is uh, very is very high, leading power factor. In case of uh, a capacitor, the leading power factor is there. You know that normally in the high voltage, or no, sorry, normally in the power system, the power factor is lagging. But if you have only capacitor to be tested from a transformer, the current drawn by the test transformer will be capacitive. Let's draw it. What happens? You have, sorry, yeah. So let's say this is the, we begin with the voltage U2, that is the output voltage. And the this is I leading, I capacitive, you can say. And let's say the capacitive is not 100% capacity. There will be also some resistance, and there is a current of this order. This is, you can say, IC of the drawn by the test transformer, drawn by the capacitance formed by the insulation you are testing. So you draw a parallel line here to this, and this is your you can say IC R. This line is parallel to this line, isn't it? The resistive drop in the active power loss, you can say, or the resistive current loss, or loss in the, yeah, that can be determined. And then you make the over the capacitive reactance, that will be this way, isn't it? Now at 90 degrees to this. So this angle is 90 degrees, and this gives you ICXC. Then you draw the input voltage. That will be given by this arrow. So this is your U1 on a transformer. If you were drawing, let's say, if you had a transformer and you are applying the voltage to the test, this may be grounded, and this may also be grounded, and this is your IC, and this is U2, and this is U1. That is what we have drawn, and this is forming a capacitive reactance XC and some resistance in the capacitor will form a very high resistance, in fact, but because the IC is very small, so ICR drop is very small. And basically IC XC drop will be there very high. So I've drawn a little bigger ICR. Okay. Mm. Now, what do you conclude from this diagram? If the output voltage gives you higher than the input voltage, if you just apply the turns ratio, multiply the two, the uh, output voltage actually for a capacitive current drawn by any load, the voltage applied reaching the capacitance is higher than the voltage applied to the capacitor. Yeah, this is the voltage applied with the help of the transformer, as you can see it here. Is the U1 is the voltage applied with the help of transformer, and U2 is the actual voltage across the capacitor, which is higher. And if you had calibrated now U1 uh, with respect to U2 with the help of turns ratio, the what you would read at U1 to be smaller than actual voltage being applied on the capacitor with the help of turns ratio. What do you call it? Ferranti effect. This is very well known for open circuited transmission lines, because the transmission lines form a very high capacitance under this condition, and so the far end voltage is higher than the sending end voltage that you must have learned. So the technique of calibrating the primary side of the transformer would give you misleading magnitude of applied voltage on the test object. This is the test object. You can say this is the test object. So the simple technique of calibrating the primary side of the transformer is not valid in this particular case, because high capacitive current is drawn by the transformer. So you have to apply, you have to measure. What do you conclude from here? That you have to measure from the secondary side, and to be having a, in order to have an exact knowledge of the magnitude of the voltage applied to the test object, which is your aim, you must measure always on the secondary side. And the secondary side voltages, the test voltages are very, very high. We have already learned about. So all new and different techniques have to be applied for the measurement of high test voltages. Earlier, which I'll be talking a little later, very accurate method of measurement, that is the construction of construction and operation of electrostatic voltmeters. The electrostatic voltmeters, which are based on the force between the two electrodes in uniform field, have been used very widely, but not to very high voltages, because the size of the electrostatic voltmeters, that is the plates between which the force is measured and calibrated to the applied voltage, was this was practiced to something like few hundred kV for the measurement of few hundred kV power frequency voltage, and also DC voltages. But because of its size, that is no more used, and other complications were also there. It is not electrostatic voltmeters. I have come across, I have used them in high voltage laboratories, but their use is slowly going down. Then there was a very widely used technique of measurement of high voltage, that was measurement with the help of sphere gaps. You might have seen in the laboratory very large size spheres made out of copper, two spheres. On the upper one, you apply the voltage, the lower one, you ground it. And the characteristic of sphere gaps is that they form if the gap distance is not very large and the size of the sphere, that is the diameter of the sphere, is adequate. There is guidelines for that. The field developed between the two spheres is weakly non-uniform. And the characteristic of weakly non-uniform field is, like in uniform field, for a given gap distance, it will always give you a breakdown at the specified voltage for a given gap distance. So that the sphere gap characteristic of breakdown, that breakdown with increasing gap distance have been standardized, have been plotted for not just one type of voltage that it was applicable for AC Prof, you can see DC for lightning impulse, for switching impulse, and then the effect of polarity for different polarities of the voltage. You have the tables, you produce a breakdown, you know the gap distance, so you can know the voltage at which the breakdown has taken place. So this was a little cumbersome process. Standard tables are available, still available. You can find in standards, specifications, and in the books for every possible condition. That means for different size of the spheres, for different gap distance, the breakdown voltage measured for AC, for DC, both polarities, for lightning and switching impulse voltage of both polarities. So how many tables does it make? Two for DC, two for lightning, two for switching, six, and one for AC power frequency. 7 tables for different sizes of the spheres. Standard sizes of the sphere may be varying from 25 centimeter diameter to even 1 meter diameter of the sphere. Imagine 1 meter diameter, such huge spheres, and calibration has been done. But there were two disadvantages. One, that every time you want to measure the voltage, you fix a gap, then you produce a breakdown. Without making a breakdown in the air, you cannot know the magnitude of the voltage being applied. Secondly, because of all these process, sometimes dust deposition, sometimes the atmospheric conditions changing, the accuracy of this type of measurement was inaccuracy was 3%. 3% inaccuracy is very, very large. So we'll talk about voltage measurement by sphere gap a little later. Then comes the it was desirable, but we'll be talking about to not just measure the for particularly AC power frequency, not just measure the RMS value, but the peak voltage measurements. And you can imagine in case of lightning and switching impulses, it is the peak voltage which needs to be measured. So the techniques of or methods of peak voltage measurement became very important, and the peak voltage measurement circuitries we'll also study. And then we'll begin with the principles of types of voltage divider. See, the voltage divider, that is a very, very accurate technique to measure the voltage on the secondary side, that means on the high voltage side, with the help of dividers. You divide the high voltage to desired level where you can measure it. And voltage dividers lately have come up of many types, and they are most commonly used in the power system network. If you, if I put the, yeah, here, this is what we have talked about. High voltage measurement technique for AC power frequency, as you can see it here, AV, AC power frequency. The primary side we discussed, uh, you primary side of the load test voltage measurement, obviously RMS by calibrating just the dial. And then sphere gap we talked, we'll go in detail. Electrostatic voltmeters were practiced earlier very widely. We'll talk about it also, what it is. Then series impedance and ammeter. That is a technique. You put an ammeter in series, obviously, to measure the current. You always put in series with a over a series impedance applied to the high voltage. So you measure the magnitude of the current, and that is then calibrated to give you the magnitude of the voltage. Potential dividers and oscilloscope, and with the help of oscilloscope and potential dividers, as I said, we will be talking about this first. The types of potential dividers and the measurement techniques. Then for the techniques of peak voltage measurement, peak voltmeter with dividers have been used also, that we will be talking about also. Then the techniques applied, see, you saw so many variation for the techniques applied for the measurement of AC power frequency. And the constraints we'll be also talking about. The DC voltages, the sphere gap can measure the DC, as I mentioned. Then series resistance and micro ammeter, and you put a very high value resistance in series between the at that point of high voltage, and the micro ammeter will give you the current passing through this resistance, and you can know, then you can know the voltage applied. This can be applied in DC. Then we have resistive potential dividers also for impulse voltages, for lightning and switching impulse voltages. We can use all these techniques: resistive voltage dividers, sphere gaps, potential dividers, oscilloscope, and peak voltmeter with the series capacitor and potential divider. And the types of dividers are so many types of dividers we learn in the next. Okay. Yeah. We have discussed most of these points. Another, as I said, when you apply a voltage on a test object, you would like to make measurement continuous measurement. That means you, at every instant, you must know what is the voltage being applied. So a continuous measurement of variable voltage is needed. That is what is the prime aim for the measurement of test voltages in the laboratories. So I think we have talked about most of the points mentioned out here. Let me check if I have now. Yeah, the measurement technique you adopt is the question of cost, convenience, and also the accuracy of measurement you desire. The simple arrangement would have been you calibrate the low voltage measurement dial with respect to the high voltage on the transformer, but that is not accurate way of measurement, as I mentioned in our particular requirement. Then safety also plays very important role when you are making measurement. Accuracy, safety, and convenience, all these things play important role. And the complications in measurements increase with the magnitude of the voltage desired to be measured. The problems confined mainly with respect to the large structures. You can imagine when you have to measure something like 1800 kV or 7200 kV impulse voltage, as we have learned about the test voltage equipment. So when you produce such equipment producing such high magnitude of test voltage, you must have provision for making the measurement. Otherwise, how can you know what is voltage you are applying on a test object? When such high voltages are to be measured, the measuring device itself acquires very high size of the whole equipment. So sometimes the measuring device may be as big as that of the test equipment, isn't it? So the uh, yeah, what happens here? Large, yeah, when you are measuring uh, uh, such high voltages, the stray capacitances also pose problem in the measurement. What is stray capacitance? You see, uh, for example, I'm sitting here. Is there a capacitance formed between me and the wall at the back? Will there be a capacitance formed? Yes. What is forming the capacitance there? The air in between me and the wall. Same way, between the test equipment, between the measuring equipment and the surroundings, stray capacitances are formed. And these stray capacitances also disturb, give disturbance in accurate measurement. So stray capacitance formation is a big uh, problem. Yeah, then protection when you are dealing with such high voltage, the manpower protection and equipment protection is always there. Uh, then uh, for the large structures are required to control the electrical fields. Yeah, as we have been mentioning, you can make a connection of high voltage with just a simple thin wire. But when you apply very high voltage to the thin wire, there will be partial breakdown around it because of the high field intensity. So, what is the solution? To bring down the high field intensity when you are using the connection for high voltage, you have to increase the size of the connector, the metallic connector with which you are connecting. You have to increase the diameter, you have to increase the resistance of, you have to increase the radius or the diameter of the connecting uh, you can't say it wire anymore, because wire would not be used. So you take pipes, very big diameter connecting pipes are used. So there are donut rings. They are kind of dome shape electrodes and all that we have been seeing are used. The size of the electrodes is increased to bring down the partial breakdown around the conductor, because it reduces the field intensity, so the partial breakdown is not able to take place. The location and layout of equipments is also very important to avoid stray capacitances between safety and stray capacitances and partial breakdown taking place at high voltages. All these things have to be taken care even for the measurement techniques. Then electromagnetic fields, that is what we are talking. That is, if at any joints or at any place partial breakdown is taking place, EMI, electromagnetic interference, may give rise, and electromagnetic fields or electromagnetic fields, one should not say, because there is nothing like it, electromagnetic fields. Electromagnetic interference may, may take may take place. There is nothing like electromagnetic fields, mind it. You can learn about it more. Hmm? Problems in measurement of impulse voltages and currents, and these should be minimized. Whenever a partial breakdown measurement or measurement of impulse voltage measurement, there may be EMI, electromagnetic interference, because of the electromagnetic signals are produced, and that should be minimized. The high voltage measurement technique in electric power system are different, as I mentioned right in the beginning. In the power system, the techniques acquired are completely different. The measurement of continuous voltage is over the CTs and PTs, the current transformer and the potential transformer, and there's not that much of complications, because there is a system, and the level of voltage is also lower, because level of test voltages is always much higher than the uh, rated voltages. So these things, these precautions and these techniques accordingly come into picture. And yeah, we will uh, we have talked about the high voltage, what are the different techniques utilized for different type of voltage measurements, and then uh, we 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 can talk about here that the yeah, we have discussed that earlier techniques were sphere gaps, and they are no more. You may see in even in my high voltage lab in IIT Kanpur, oh, there's a big sphere gap, but it is never used, because those techniques have been given up. They are not accurate, as I mentioned right in the beginning today. Sphere gap techniques are not used anymore, but the sphere gap are symbol of high voltage laboratory. So they are still kept as an antique ornament in many of the labs I have come across. People don't want to throw it away, because that gives you an impression of, or an idea, that this is nothing but high voltage laboratory. So for the identity of the high voltage laboratories, the sphere gaps are still placed at some corner in the laboratories, but they are not used anymore. Yeah, for education purpose, I mean, you can produce nearly uniformly for a small gap distance, for sphere gaps having very large diameter, and you can experiment. You can measure the breakdown strength, and students would like to perform the experiments and measure, and consistent results are there. So that can be used for experimental or high voltage experiments to be done by the students. Hmm? Uh, I don't know how many of you have come across or visited high voltage lab, and how many of you are will be able to perform experiments with high voltage in the laboratories. But that sphere gaps can be used uh, for this purpose. Then we have uh, the disadvantages we were talking about. I have mentioned 3% inaccuracies of the order of 3%, and every time you have to produce a breakdown, which is not desirable for the measurement. I mean, breakdown you can observe, you can experiment by producing breakdown, but every time breakdown to be produced for the measurement is not desirable. Another thing, the sphere gaps won't provide a continuous measurement of the applied voltage on the test object. The sphere gaps will not be able to give you an idea about the continuous voltage being applied on the test object. You can uh, know the magnitude of the voltage applied only when you produce breakdown in the between the two spheres. Electrostatic voltmeters uh, suitable for AC power frequency and DC, as I mentioned, is one of the most accurate measurement, giving you the peak value, or you can convert into RMS. Due to this gives you RMS value exactly. We'll see that. However, due to its size, cost, and adjustment problems, it is also not used very much. The primary side measurement we have also talked about is not done in the transformer, because we discussed it, penalty effect and everything in detail. Then the techniques could be give rise to error in two ways. For we have discussed about high capacitive load, the Ferranti effect, and all that. This is we have also finished. The uh, the second disadvantage of measuring from the primary side, uh, that may be okay in laboratories where you don't need very high accuracy in the applied voltage on the test object. People may be practicing it, but that doesn't give you a very good measurement, very accurate measurement. That simplifies many things, but when you want to do, don't compromise with the simplification. You want to do it of high quality. Any action, it requires efforts, not only efforts, it requires techniques, efforts, cost, everything together. So uh, I was wondering, yeah, we can talk a few minutes more. Yeah, principles of, as I mentioned, we'll talk first about the uh, measurement technique with the help of potential dividers. That is the technique used most commonly today, which is an advanced way of measurement of high test voltages and applied everywhere. So, the for the measurement of high voltage of any type. The best part is for any type, best technique, the most advanced technique is by dividing the high voltage into a low voltage level suitable for the instrumentation or the measuring circuit where it can be measured directly. I mean, at the divided value of the voltage, which we divide it to the extent that it can directly be measured with the help of potential dividers. High voltage potential dividers, uh, divider arms could be pure capacitive, as you see here. These are the high voltage. These are the here, as you see, this is a high voltage potential divider circuit analysis. We'll do it next. And this high voltage potential divider, this Z1 and Z2, that is impedance being shown. This could be high resistive divider, pure uh, resistance. I mean, Z1 and Z2 could be formed with pure resistance that is suitable for DC measurement. Then we have low resistance divider. Um, uh, yeah, low resistive divider for it for lightning. Correct. This is, as you see, low resistive divider. That means the division ratio should not be very high for lightning impulse measurement of high lightning impulse measurement. You can use resistive divider, pure resistive divider you can use. Then capacitive dividers for AC and switching are used. As you see, the Z1 and Z2 are two different values of yeah, I mean Z1 impedance and the Z2 impedance. They are formed out of capacitance. So capacitive voltage divider, and these are suitable for AC power frequency and SI. Why capacitive value? Why not resistive potential divider for AC and switching? Because the formation of stray capacitance play a very important role in case of slower wave shapes, that is for AC power frequency and switching impulse voltages. So capacitive voltage dividers would give you higher accuracy. So, and the resistive voltage dividers would not be suitable. Then you can, people have been inventing new things every day. So damped capacitor dividers for, again, the switching impulse and and AC power frequency. What do you do here? That with the uh, capacitor, you put another resistor also in both Z1 and Z2 form with the help of capacitance and resistance. So that is called damped capacitive divider. That is also used very widely now. And universal divider for all voltages you can have. This is also a circuitry of damped capacitor, a capacitive divider. This is a combination of capacitors and resistors. The last one, universal divider, which can be used for all types of voltages. So different voltage dividers have different uh, different division ratio between Z1 and Z2 are being used uh, these days in the laboratories. And you can imagine that uh, on the high voltage side, that is the topmost side of this divider, the highest voltage is to be applied. And when, say, 1000 kV or 1800 kV is to be applied, the size of these dividers would be also very, very large, as large uh, maybe as that of the equipment. So this is we will analyze in the next lecture. This is the typical connection diagram between the for a potential divider circuit. So this is the high voltage B is being applied at this is the high voltage being applied, and high voltage is being applied across the Z1 and Z2 combination. After Z1, the connection is taken with the help of a cable, coaxial cable, and coaxial screened cable. You know that for the measurement, and it comes to the uh, oscilloscope and the voltmeter here. Here you can put the oscilloscope and the voltmeter there, where low voltage of the order of few hundred volts is reaching to these measuring instrument. Oscilloscope and voltmeters are the measuring instruments. Here, two things play important role. As you can see that this is between the high voltage and the low voltage. This is between the high voltage and the low voltage. Stray capacitances are formed. Whenever something is on high voltage, between the high voltage and the low voltage, or the ground, low voltage you can say that of the ground, stray capacitances are formed. And there will be also the oscilloscope will have its own impedance. Then there will be some more impedance formed, measured across the voltmeter. I mean the effective impedance measured across the voltmeter. We can say Z prime, Z2 prime. This Z2 prime is the measured Z2 prime is measured across the voltmeter, or which is influenced by the impedance of the cable itself. See, this cable is bringing the voltage. It'll have its own impedance also. So all the stray impedance, the measuring circuit impedance, all together determine the value of Z2. So that we will analyze in the next lecture, and I think we have, yeah, but today we will, let's call it a day, and we'll begin with the voltage dividers, the different types of voltage dividers. How do the in the voltage dividers, you can imagine the main thing is the high voltage arm of the divider, that is Z1. The Z1 is very important, how it is formed. And the Z2 and the other things are at low voltage, so there is more flexibility there, but the design and fabrication of the Z1 arm, the high voltage arm in the potential divider, is very, very important, and we will discuss that in the next lecture. Thank you very much for today. We'll see in the second lecture of chapter 8